In this video, I talked to Philip about how to calculate and design a patch PCB antenna. Here it is.
I'll just go through what a microstrip patch antenna is just briefly, and then we can calculate the dimensions of this and see if we can fix it to our system. So yeah, it's basically a PCB-based antenna. It's just this rectangular patch over here. And I got a lot of this information also from antennatheory.com, which is a pretty cool website, not just about microstrip patch antennas, but different, Vivaldi antennas and God knows what. So it's this rectangular patch. We have a length and a width, and it's fed by some sort of microstrip transmission line, and there's many different ways to feed it, and we'll look at that later. Essentially, the main defining characteristic of this antenna is actually the length. And this is what then supports a half wave, or supports a standing wave, and it is a half wave dipole. So the length will actually turn out to be somewhat close to half a wavelength. So that's really pretty good. We can really, by this dimension, see, okay, what is kind of operating range of this antenna? It's low cost because we're basically just using, the copper on the PCB, we're using the substrate, so we don't have to add additional costs for a chip antenna or connect or something like that. And it's actually fairly easy to design from what I've seen. It's useful because of the size. Basically, L will scale with depending on your wavelength. So if you have, 100 kilohertz or megahertz design, that's going to be a huge antenna. But luckily for us, for the gigahertz region, where it's going to be like a couple of centimeters, tens of millimeters. So that's why this was also a pretty good choice for this project. The performance is okay for what we need. So these are quite a lot of different figures. We have the gain plot, or the return loss plot versus frequency, the antenna radiation pattern, and so forth. But the main takeaways for this antenna, it has a fairly narrow bandwidth. So if you're tuning, your lengths are a bit wrong, you might fall out of the band. And so that's indicated here. And typically you can expect about 3% of the center frequency to be your bandwidth. So 2.4 gigahertz, what's that, about 70 megahertz bandwidth, if you get it right. So you have to be fairly precise with those, anything. The gain
but
is
for
about
Wi-Fi, is not the bandwidth a little bit wider?
I believe so, but it's still, that's at the minus 3 dB, so hopefully it should still be in range. I've seen this used for Wi-Fi and Bluetooth before in various papers, and you can increase the bandwidth by various means, so increasing the distance to the bottom ground plane, by playing around with the widths and so forth, so you can get a wider bandwidth than just, for example, 70 megahertz or so. There's a few papers I've seen that confirm this also with Wi-Fi and Bluetooth, that this is actually a suitable design.
And this graph is showing antenna for like 93 megahertz frequency, correct?
Yeah, something like 95 to 100 megahertz. Okay. This was actually also on Antenna Theory. They designed
97 probably, sorry.
Yes, something like that. So that's the return loss. So fairly okay gain. I believe S&D chip antennas can have up to about 20 dB of gain. So it's not the greatest performing, and it's not very high power or anything. And you also get certain radiation patterns. So you get essentially a linear polarization. So it's along this length of a patch, you actually get the standing wave. There's actually quite a nice demonstration if you actually feed it. So I can show this YouTube video, what the fields look like under this patch antenna. I think it's quite a nice little visualization of the waveform itself. So there's quite a lot of information on the internet, how this standing wave, how this antenna works, and what the fields are and so on, but won't go into too much detail in this video. So yeah, so it has a couple of advantages, that it's cheap, but it's easy to make, but of course there's quite a lot of disadvantages because it is so simple and it's a fairly restricted design. So as I said before, basically you want to determine two lengths. So that's first of all this kind of length here, and also this width initially. Once we've done that, we want to provide some sort of matching mechanism, and then a microstrip transmission line. If we look at the side view of this antenna, we essentially have a two-layer board, and for reasons we'll talk about later why a two-layer board might be preferred for this design. Essentially, we have the patch antenna and the microstrip feeding into it. We have a dielectric substrate with a certain permittivity, and we have a certain height with a solid ground plane underneath. And the permittivity of the electric material and the height above the ground plane will play quite a bit into the design, and we'll need to use those values a lot to do our calculations. So I've gone with a standard 1.6 millimeter two-layer board with a permittivity of about 4.5. So 4.6 is usual-ish. For my manufacturer, that's about 4.5 they quote. Now, given that this is a microstrip, it's not completely, the microstrip isn't embedded in the substrate. Some fields will be in the air and some fields will be below in the substrate. So you can't use epsilon r directly. So you need to calculate the effective permittivity of the air, and there's calculators online to do that. The only problem is you kind of need to know your width of the trace beforehand, which is a slight catch with calculating the effective permittivity.
Okay.
Luckily, with the microstrip antenna, the first thing you actually do is calculate the width before the length. So that you can then figure out the effective permittivity. So that's a bit of a catch.
Okay, so you need to use the width of the antenna, not the width of the line connected to the antenna.
We'll have several times where we'll need to actually calculate a different effective permittivity. One is for the antenna because it is so wide. Then we'll have some sort of feeding network we'll have to recalculate. And then we have the microstrip, the 50 ohm line we'll use, and we'll have to recalculate it for that as well. So it turns out we have to do this calculation quite a bit.
Okay.
But luckily there's, calculators online, or Saturn PCB design kit toolkit and do it. But this is, I guess fairly standard procedure for microstrip transmission lines.
So can we have an example?
Yeah, sure. So I can just Google effective dielectric constant calculator. Looks like I Googled that recently. So let me see if we have something. Okay, so I can type in my board's nominal dielectric constant. So that was 4.5. Width, let's say, I know for a board, just for an example, this is the part where you actually need to know the width beforehand before you can calculate the dielectric. Let's just say a millimeter in width, and our height is 1.6 millimeters above the next reference plane, which for two-layer board will just be the bottom layer. Then we get a width to height ratio, which is important for the calculations, but not for us. And we get an effective dielectric constant, 3.15. And that's the constant you would then use in your calculations. And they will have to do that for the antenna, we'll have to do that for the feed line, and we'll have to do that for the microstrip transmission line. And so this is a fairly straightforward way of doing that. So basically you have to know these parameters of the PCB and be able to calculate, for example, the effective permittivity. Okay, so once you have that, or once you have a ballpark value for that, as we said before, the length on the horizontal direction of this antenna determines the frequency of operation, so the center frequency. And we said before, this will be a half-wave dipole. Half-wave means we need to use half the wavelength. So V equals lambda F, so velocity of propagation is the wavelength times the frequency, travels at the speed of light divided by the square root of the effective permittivity. And that's how we can then figure out lambda.
So how much is it approximately?
So lambda, we can actually do a calculation briefly. I always use Chrome to do it as well. Just the Google calculator. So it's 3 times 10 to the 8 divided by 2.4 times 10 to the 9 gigahertz times the square root of, what do we say? I think it was about 3.1. Yeah. 3 point something like that. So that's about what, 70 millimeters is a wavelength. So 7 centimeters. And so half of that will be about 35 millimeters. We'll actually do the calculation properly in the next slide, but that's the kind of order of magnitude. So it's actually fairly large. So if you want to make a miniature circuit, already like 3 centimeters is quite substantial. You can fit a lot of circuitry in that. I mean, also modern phones are probably in that kind of order of magnitude. So the thing is, you can't just use that calculation. That seems a bit too easy, especially for antenna design. We have fields underneath the patch antenna. Once we have, for example, a standing wave there, or voltage applied, but also we have fringing as usual. So we don't have just fields slides going straight down, but also fringing at the sides. And this means the resonant frequency will actually be shifted by a tiny amount, but it's actually the fringing that apparently causes the radiation and that the fact that this antenna will radiate. So all in all, because we have these fringing fields, we need to trim the length by a tiny amount. So we start off with this L is lambda over 2, and then we shave off a tiny amount. And there are detailed calculations of how much that needs to be. So we can actually go through the design example for length for our 2.4 gigahertz antenna. So we have a center frequency F0 of 2.4 gigahertz. We have a effective constant of 4.5, a permittivity of 4.5, which gives us, using an online calculator, 4.17 actually, as the effective permittivity. We plug all of that in. We see a wavelength that's about 61 millimeters. We take the half of it. And again, because of these fringing fields, the resonant frequency is actually shifted and we need to trim it by amount, and that turns out to be like 1.5 millimeters. So a couple of percent you have to take off. There is actually a calculator, and I found there's a couple online. If you just Google it, there's one at emtalk.com, which will calculate the exact lengths in which you need. So I've typed in 4.5. I have a dielectric height of 1.6 millimeters, resonant frequency 2.4. I click synthesize, and that gives me this length. And then later on, we'll need this width. So it's about 29.1 millimeters. I guess with manufacturing tolerances, that's as accurate you can get-ish. So we'll stick with 29.1.
How important is this input impedance?
That's going to be really important later. So luckily, this calculator calculates that for us, because it's a bit of a strange calculation to do by hand. And this will be really important because we'll have a 50 ohm transmission line feeding into this. And if we just couple that directly to a 250 ohm input impedance antenna, we're going to get quite a large loss. So we'll have to have some sort of matching in between that converts from 50 ohms to 247.5 ohms.
Okay.
And we'll come back to that in just a second. Well, later. Okay, so basically we need a length of 29.1. So that's a fairly straightforward calculation you can do with online calculators, or rule of thumb lambda over 2 and shave off 3 to 5%. Then we also need to determine the width. So the length was kind of our most important parameter because that is our center frequency. The width has, I believe, a tiny bit of an effect, but mainly it changes three things, and that's the input impedance. So if we make the antenna very, very wide, so we increase the width a lot, that'll actually reduce our input impedance. Now, if you can imagine for a width, which is probably similar, about 30 millimeters, we'll see how much it is in just a second, that's 250 ohms. So actually to get down to 50 ohms, it's going to have to be very, very wide. So quite unfeasible. It also controls the bandwidth. So there's this relationship here. So the bandwidth is roughly proportional to the width. So if we increase the width, we'll also increase the bandwidth. It turns also out that if we increase the distance between the ground plane underneath the antenna, if we increase that height, that also increases the bandwidth. And also there are equations for the radiation pattern of this antenna, and that is also influenced by the width. So actually this one parameter controls quite a few different things. And you kind of have to optimize, what are you going to prioritize? Is also a reason why a 4-layer board, with a dielectric very, very low or very close to your patch antenna might not be a good idea, because the electric might be 0.1 millimeter, 0.2 millimeters. And since the bandwidth scales with the height, you're going to divide that by, I don't know, by 10 or something, your bandwidth compared to a 2-layer board.
So on 4-layer PCB, usually you would like to remove layer 2 and 3, for example, and only leave the bottom layer.
Exactly. The problem is then you have to take into account not only the dielectric beneath, but also the core material and then dielectric beneath. So calculating the permittivity is going to be quite a lot harder if you use a 4-layer board.
Different materials mixed together.
Exactly. So that's why usually for this, it's preferable to do on a 2-layer PCB. Okay. So as we saw before, the increasing W, actually increasing the width decreases the input impedance. I know you said before 50 ohms is going to be very unrealistic. You're going to have a very, very wide antenna. The short answer for everything as usual, at the end of the day, you're just going to be using a calculator again. And as before, we can just use this Talk calculator or any other calculator found on the internet, and that gives us a width of 37.7 millimeters.
I have a question. So in this calculation, it is also considered that half of the environment is air?
Yes.
That's the effective, that's why we are calculating the effective permittivity, correct?
Exactly.
Okay.
I believe some other calculators will actually tell you the equations. Here we go. So it turns out for the width, you actually just consider epsilon r, because you have to have some sort of starting point, I guess. I guess you can iteratively do it, and then once you have the width, you can go back and calculate the effective permittivity. But all the calculators I've seen, all the papers I've seen, they start off with just the permittivity. And from that, you can calculate the effective permittivity, and from that, you actually then calculate the length. I assume to get a more precise answer, you would then, use the effective permittivity to go back and kind of iteratively, like optimization problem, hone in on the actual width, which will then give you the effective permittivity you need, and so on. But it seems like it's fine, at least for the width, just to start off in the ballpark. We know epsilon r is just considering the dielectric. But I'm sure some antenna architect could explain that a lot better than I am doing at the moment. Yes. Okay, so this calculator is what I would just go by. That includes all the calculations. It'll include the effective permittivity and so on. So this is the calculator shown, EM-Talk. That seemed to work the nicest for me at the moment. And that gave us these two parameters here. Gave us the length at 29-ish millimeters and the width at 37.7 millimeters. So fairly straightforward. We didn't have to even bother with all the calculations or wondering what does what. We want the center frequency, we want the length of which, we just plug it in, and that's it.
What's the difference between synthesize and analyze?
So we can choose, well, we have to type in the permittivity and the height. That's always a given. But we could either start from a center frequency and then synthesize that to make length and the width, or we could start with the length and the width, analyze that, and see what resonant frequency that will give us, and also the input impedance. So it's both ways. I guess it's like also like in impedance calculators for microstrip or PCB traces. I guess they always have that. At least in KiCad, that is the way. You can synthesize or analyze, and then depending on if you start with an impedance and want a width, or start with a width and want an impedance. So I guess that's the same thing for that. So yeah, you mentioned earlier that this input impedance, well, might be important, and it looks rather large, which it is. And we actually need this parameter, and luckily this calculator calculates that. So again, it's a very messy equation that calculates this input impedance of this antenna at this edge on the side here. And we need that to feed the antenna, and we'll look at that in the next step. So we saw before that at this edge, when we want to feed the antenna from our source or our receiver, transceiver, that antenna there has a very high input impedance, so 250 ohms, rather large compared to what we normally have, like 50 or 75 ohms. So a typical RF trace width, for example, our microstrip transmission line, will be 50 ohms. So if we said before, if we simply connect the RF trace 50 ohms to the antenna, it's quite a huge impedance mismatch. So we get power losses, we get reflections, and the design, as you said before, the bandwidth is already limited. If we do that directly, we'll have, nothing left. So we need something in between. Essentially, we need to match our 50 ohms, which is our trace coming from our transceiver, to the microstrip antenna. So some block in between, and that could be done with various impedance matching networks. But there's actually a couple of really interesting things you can do with one of these antennas. So these are just two different ways of doing this. There's many other far more complicated ways where you have a trace underneath the antenna and it couples to the dielectric. And I was like, okay, I just want the easiest thing. Might not be the prettiest, but at least I can be a bit more sure that it might work. So yeah, there's many different methods of matching and feeding. These are the two main ways I had a look at, which might be most feasible for a simple design like this, and without having access to simulation tools. The first one is a quarter wave transformer. A quarter wave transformer is actually really popular in RF, something that's used a lot. Essentially, if you have an impedance mismatch, so from a source to a load, you can put something in the middle that is a quarter of the wavelength, a microstrip line, a strip line, and that has essentially the geometric mean of the source and the load impedance. And that will make sure the load and sources are matched. And that's pretty neat. And you see that a lot, and you can do that a lot with Smith charts if you go to RF. And that seemed pretty straightforward. We only need to calculate a microstrip line with a certain length and a certain impedance. Another way was using this inset feed. On antennatheory.com, there are quite a lot of explanations of how this might work. I must say I did skim over it because it seemed a bit more involved than just doing this on the left with a quarter wave transformer.
Because you are also, damaging some kind of part of your antenna this way.
Exactly, yeah. And that to me seemed like, okay, maybe this is a path I shouldn't venture in just yet. Let me just get the first thing right and then see how this thing turns out on the right side. But yeah, you basically have to make these slots in the feed line, and that'll change in some way the impedance properties seen at that edge.
Mm-hmm.
And reduce the coupling, increases the coupling at certain points, and miraculously it would work, apparently. But basically what I went with, because of simplicity, is this quarter wave transformer. So before it's the easiest method, but because you are adding this length in, like a quarter of a wavelength, you're adding again size to your PCB, and it's not like it's just a millimeter or so. It's going to be an order of like 10-ish millimeters. So it's optimal for ease, especially for me, who doesn't really understand how it works. But in terms of size, it'll add quite a bit. But given that, you know, this antenna is already a bit, and it's a bit of an experiment, I thought I'd just go with this. The basic information is what you need to know. You may need to make it lambda over 4, so the wavelength over 4, again, calculating the wavelength using the effective permittivity. And then apparently the quarter wave transformer needs to have an impedance, so a characteristic impedance of this trace, which is the geometric mean of the source impedance and the load impedance, so the square root of the product.
Oh, there is something hidden in it.
Exactly. Yeah, it's quite a neat result, to be honest. You know, quarter wavelength, and then you have a product of these, you take the square root, and that seems to be it. So this is a fairly straightforward way of doing it. We also know the source impedance, which we want to be 50 ohms, and we know the load impedance via the calculator from the antenna, which should be about, what, about 250 ohms-ish. And basically, we then just plug in those numbers and hope for the best. So it turns out that the geometric mean of 50 and 248 is 111 ohms. So this trace, we have to design the width such that this is 111 ohms characteristic impedance. And it turns out we can use, for example, the KiCad calculator. So the PCB calculator on the main page. If I type in my microstrip line, I have epsilon r is 4.5, a height of 1.6, and I have 111 ohms. Apparently someone's already calculated this before. And then
Who was it?
I click synthesize, and miraculously that gives me 0.469 millimeters. So we need to make our trace width 469 millimeters, sorry, 0.469 millimeters right here. So that's where that number comes from. Again, this calculation will have included the effective permittivity of the air and the dielectric substrate underneath. And the quarter wavelength, again, using the same effective permittivity will be...
You use now here the effective permittivity 3.055, and...
Yes, because yes, exactly. Because it's dependent on the width. Because the microstrip antenna was so wide, it had a higher effective permittivity. It was like 4.17 or something. But because this is considerably narrower, we need, you know, a low, and that is the annoying thing about the effective permittivity. You can't just say, okay, we have this much, well, you have to say we have this much air and we have this much dielectric medium underneath. We have to look at essentially, yeah. So that's why it depends on the width, and what makes this whole effective permittivity thing quite annoying to calculate. But yeah, we actually get quite different values. So from 4.17 to about 3.1 is quite a jump. So yeah, so that turns out it needs about 18 millimeters of length. So 2 centimeters, that's quite considerable to add to a PCB again. So that's why this design, even at 2.4 gigahertz, which seems like a fairly high frequency, at least for fairly common designs, that's, you know, quite considerable. Okay, so basically we've done the antenna. We've calculated the length and the width. We calculated input impedance. We know our source impedance. From that, we did the quarter wave transformer. The last thing we need to do before we feed into our circuit is essentially the microstrip transmission line, which is our 50 ohms. So thanks to the quarter wave transformer impedance, we don't have to worry about, okay, are we doing any more matching? No, we just do a 50 ohm line. And again, we use a calculator, and I'll just go back to the KiCad calculator. We want 50 ohms. So 50 ohms for the same board specs is about 3 millimeters, so which is huge. Like if you imagine the ESP32 is like a QFN 48 package, so a 0.25 millimeter pad width, and we have to go out to 3 millimeters. That's mental. So another way we can do that is with a coplanar waveguide or a coplanar waveguide with ground to try and reduce that track width a bit. So coplanar waveguide with ground, down here, we can actually type in some different numbers. So we have 50 ohms, synthesize again, and we also need to take care, of course, of the spacing. So we have ground next to our trace, so we can pull that further apart or put it closer in. Again, we want to, I guess, keep it fairly close so we get a smaller trace width, but that also depends on our manufacturing capabilities. So I've set it the space width about 0.2 millimeters, and that gives a width which is about a third of what we would have without this coplanar waveguide. So 1.08 millimeters. So yeah, you can use the 3 millimeters if you maybe have different components, but from a QFN, it's a huge like branch out. I mean, I guess you can do it if your distance is very short. So if you do a very quick increase over a short distance, you will have, you know, we have an order of wavelength about 20-ish millimeters, if not more. We can get away if we just do it over like, a couple of millimeters if we do that expansion. But still, it doesn't look very pretty if it's 3 millimeters.
You still may need to connect the neighbor pins somehow.
Exactly, that as well. Yeah, and that we'll see later also in the design is a bit of a headache trying to squeeze in decoupling capacitors next to a coplanar waveguide trace. So that's another thing. Pretty much the last thing is also that we need a ground plane underneath. So it's not just that you need a ground plane directly underneath the antenna, so a ground plane that just stops here and here and here. It's because we have this fringing effect. So the fields don't just exist underneath the antenna, but they also expand out. So in this direction on all 4 sides of the antenna. For that, we need a minimum size of the ground plane underneath. So we can't just, make an antenna a certain size and make the PCB the exact size, trying to save as much space as we can. We actually need to increase the ground plane underneath by a certain amount. And from various papers and calculators and so forth, the general rule of thumb for the minimum dimensions of the ground plane underneath seems to be the length of the antenna plus 6 times the height of the dielectric material. So 6 times 1.6 millimeters in our case, and the same calculation for the width. And that seems to be the general guidelines, general rule of thumb. Yeah, so that's the last thing, the last part of the puzzle, so to speak.
So if it's like 1.6 multiplied by 6.
Exactly, plus the length. I actually have the numbers in 2 slides. We can see how much that actually is.
Okay.
Yeah. Again, the last thing is why we need a 2-layer PCB after we've seen all these design steps. It actually helps a lot, and it makes the design process a bit easier. We first of all, with the greater dielectric thickness, we get an increased bandwidth. It's directly proportional, and we get an increased antenna efficiency as well, it turns out. Another thing is with the manufacturing tolerances for 2-layer PCB, because we have these wide tracks, because we have such a large separation between, the top signal layer and the bottom ground plane, that will give us wider tracks, which sometimes can be annoying for certain packages, but also the same manufacturing tolerances apply. So a plus minus 0.1 millimeter change for a 3 millimeter track, you're going to get a plus minus 1 ohm impedance change. Whereas for a 4-layer PCB, where the dielectric space is like 0.2 millimeters, if not less, it can give maybe even plus minus 10 ohms for that same manufacturing tolerance. So in that case, RF PCBs, a lot of the times 2 layers is actually not a bad choice. Yes. So here then is the final design. So this is the footprint. Basically, we can go through it later actually. I made the footprint in KiCad. It looks huge if we look at it like this. We have the antenna on the right side here with a length, of 29.1 millimeters, width of 38.7 millimeters. The ground plane needs to be 38.7 millimeters actually, and 47.3 millimeters. And that was that
basically
calculation.
The component is even bigger.
Exactly, yes. And we'll see that in a second with the PCB, how far the ground plane needs to extend out. So plus 6H, essentially, all around. So and then the quarter wave transformer is this rather thin trace in the middle, and that's at 18 millimeters with a certain width. And then I just added this tiny, it's 1.08, I believe, width trace. This is the 50 ohms that will then narrow down and feed into the QFN package. Another thing about the 4-layer boards is actually this trace, this quarter wave transformer, was 111 ohms, I believe.
Yes.
So if we try to do a 111 ohm trace on a 4-layer PCB with a dielectric spacing of 0.2, let me just pop that in the microstrip. Whoops. 111, is that all right? It doesn't want to accept it for some reason. There we go. That's a 0.043 millimeter trace. Another reason why, in this case, a 4-layer PCB with such a close dielectric spacing wouldn't have been too great. Of course, you can, avoid the ground plane.
I don't think you can manufacture this.
Exactly, it's a crazy. Yeah, it's ridiculous. And also, that would look great, like a 0.004 millimeter trace going to this huge antenna. But yes. No, so I mean, you could void the ground planes and so forth, but then you have this mix of dielectric material of the prepreg of the core. So, yeah, in this case, the 2-layer was, in my eyes, better. Okay, so I guess we can jump over to KiCad and just have a look at the design, if you want.
Yeah.
So the final design, I don't know. Have you watched Dodgeball? The film? Okay.
Yeah, I did. Yeah, I have.
With the guy in the wheelchair who's the coach?
Yes.
Patches O'Houlihan. I guess that's the, micro Patches O'Houlihan is the antenna. It always comes to my mind, that film, when I see anything with patches. But anyway, this is the huge patch antenna. So it's a 2-layer board. This dimension here, and essentially this dimension, is the ground plane underneath. So I've drawn in the dimensions in KiCad. We have the antenna width, 29.1. The antenna length, 29.1, antenna width, 37.7. And this ground plane, 51 millimeters, is actually the minimum required ground plane. So ideally, I probably should make it, wider, but this is the minimum accepted. And then 80 millimeters for the whole length of the PCB. That includes tightly fitting all of this essentially digital electronics, doing this quarter wave transformer in this pad. So
it's quite long, yeah.
It's quite long, 80 millimeters and 50. So it's not the prettiest PCB.
It's
but
like
it's
80 millimeters. It's like this.
Yes, it's quite a big, and also in comparison, I wonder if I can actually, I don't know if I have a ruler here to make it the same size on my screen, but it's considerable. It also looks kind of ridiculous if you compare that to all the electronics over here. But it's something I'm having produced and trying to see if this will work, if I can even, if the remaining circuitry in the ESP32 works, if I can connect via USB, if I can program it. So even should the antenna not work, I hope I can still at least program it and get some things to work. Okay, so I mean, a couple of things.
By the way, don't forget, but I'm actually working on a video with KiCad, and we are going to measure the Bluetooth Wi-Fi antenna.
Oh, cool. Okay.
So maybe if you make a software or something which would do something, I could send it to KiCad.
That would be awesome.
We could measure it.
Yeah, that'd be great. Definitely. What time frame is that, do you think, with the video?
I think we are going to record the video sometimes in 1 month or something like that. I don't remember exactly. Okay,
well, hopefully I can get something up and running till then. But if it works, but yes, that would be cool. That'd be really cool to see. Yeah, that's another thing, right? Having just the tests up and the gear to be able to then actually perform some proper tests, rather than I can transfer something at a certain speed, and certain if I hold it this way it doesn't work, if I hold it this way it does work.
I remember this kind of testing. Yeah, we went to the other room and it's still working.
Yeah, exactly. It must work. It passes all tests. Yes. So I will be performing similar testing in my huge laboratory at home with this device. But let's see. At least the calculations seem to match up with what papers say and so forth. So that's my only hope now. But yes.
Yeah. Okay, so you can continue. I interrupted you.
No. That'd be cool to do though. Yeah, I mean, with the PCB design, there's nothing special about it. To have via stitching, because in this part on the right here, well, you see all these vias. I have a ground plane on the top as well. I voided all of the ground plane on the top layer around here because, of course, that will change the impedance. It will change the resonant frequency. You want this area clear of also solder mask pretty much. And but
there is still a ground plane on the bottom.
Yes, there's still a ground plane on the bottom. I think I can show this here. So yeah, like this. So green is the ground on the bottom, and red is the copper on the top. Stitching vias, for example, here, at that kind of boundary between the digital side and this RF side, I went with, the usual recommendation, 20th of a wavelength. So the spacing here is about, I don't know, what's that, 0.9 millimeters? Something like that. So just general rules of thumb, try to follow and try to maximize the chances of success of this thing actually working.
And in the space, they are a little bit further from each other. In the empty space.
Yes, exactly, yes. So just in the boundary, I thought, this is kind of the boundary between the RF and the digital part. The actual stitching here, I don't believe has much of an effect. Essentially, the RF section is just along this with this little bit over here. Other than that, this board isn't particularly exciting, to be honest. It was mainly a test for this patch antenna, USB-C connector, ESD protection, USB to UART bridge, little voltage regulator and so on. So that's all there is actually on this board. And this is just to test the antenna, test in quotes, of course, and the USB connector. And we can go through the schematic briefly, if you like.
Okay, another question. So, are you going to like connect two boards together, or how are you going to test the antenna? What kind of software or data transfer you would like to
So
do with
ideally,
this?
I would just like to. I am rather unfamiliar with ESP32, so I'm not entirely sure what all of the capabilities are. But essentially, if I can just get data streaming between, for example, my local network from sort of a host computer via Wi-Fi node onto the ESP32, similar thing with a Bluetooth connection.
Okay.
If I can get something like that running, my laptop surely has Bluetooth, and that'll, I can set up some sort of communication in that sense. That's what I'd like to. I mean, it would be interesting to have two boards try and communicate with each other to see if that works. I guess transmission, reception tests, if it works better in certain directions or if it doesn't, I'm not also sure what transmit and receive powers you can, or transmit powers you can set on the ESP32, if that's a variable thing. I wonder if somehow from that you can infer, how your antenna is performing, or doing some sort of indirect tests.
How do you write this software? Are there like libraries and you use the library like Connect or Discover, or I don't know exactly how it works?
Yeah, from what I've seen, so I think there's two main ways people do it. There's this Espressif, I'm sure I'm pronouncing that wrong, but it's the company that makes these ESP32s, and they have a free IDE called the IDF. So you can either use that and then use the libraries they provide, or open source libraries, or you can also go the Arduino IDE route, which seems to be, the easiest route just to get something up and running. And I believe, as you say, then it is just, okay, connect certain node. Here's maybe the IP address, or here's the port number or name, and then you just send a string or receive a string and so forth. So I think all of that framework, at least compared to the STM32 side of things, should be all in place already.
Wow.
But
and everything what you get basically are just serial data through USB.
I think on the most basic level, yes. I'm sure you can maybe change that, to whatever your needs are. The Wi-Fi thing might be more involved than just receiving serial data. But on the Bluetooth side of things, I believe that's how it functions. I will try to be making some videos of my own discovery of ESP32 and seeing how that works, similar to STM32.
So what do we have in this schematic?
So the schematic is fairly simple. Luckily enough, there's always reference schematics. So there is something called the Pico Kit D4, something along those lines. And basically, you can either use the datasheet or something like this. And a lot of it is taken just from a reference design, because that's just always the best place to start, in my eyes at least. So it has the same thing, UART bridge, it has a regulator, very simple, nothing switching, the ESP itself with its various connections, and some buttons. So what you see there is pretty much what you see here. I've added some things, for example, USB-C connector instead of just a micro B, because that seems to be the fad these days.
So when it is micro B, it means you can only plug it.
Yeah. So
how is it done? Because normally there are connections from both sides, no?
Yes. So this connector, so there's many different USB-C connectors. There's one which only do power. There's one which do, USB 2. There's one which do USB with super speed on it. So this is the one you can actually flip around on both sides. Let me just show it here. So it's a plug in from both ways. So which routing wise makes you do some naughty things, which I can show in a second, which you create little stubs to connect the two D- lines
I see
together.
A7, B7, okay.
Exactly. So the routing isn't optimal. Also on a 2-layer board, you're not going to get 90 ohms differential traces, that easily. But I've committed a sin and haven't routed them as they should be according to the USB spec. But yes, I've done that many times and it still works. So yeah, so basically you always have the double pins. You have 2 communication channel pins, 2 sidebands, 2 V-bus, 2 grounds, 2 D-, 2 D+. And then you just have to connect some of them together. For example, the communication channels, you have to keep with separate resistors. And if you just connect these 5K1 pull-down resistors, you basically can negotiate, if the host can do it, to about 1.5 amps at 5 volts. So plenty for this design. But this is just my standard, 2 resistors, USB-C connector, and this works for USB 2 and power delivery. Then just ESD protection for the sake of it, a little bit of bypassing. That feeds the regulator, so completely USB powered. making sure not to exceed the USB spec, you know, routing my differential pairs as they shouldn't be, but then trying to keep within spec for the decoupling capacitors. So less than or around 10 microfarads of the input, tiny bit of filtering, and a pretty overkill regulator as well. I mean, this can do about an amp, I think, this regulator. And yeah, just a little status on LED. And the rest of it is basically the minimum configuration this ESP32 needs to boot up. So you have various boot pins, which can put into boot mode. So via tactile switch or dip switch, you can change those, enable all of the various bypassing, decoupling, and the USB to UART bridge, which is actually one of my favorite chips. It's a CH340E, and they're really, really cheap Chinese USB to UART converter. So they require an extra driver, so not like FTDI, but they're like 80 cents and they work pretty much instantly. Don't require external crystals and very minimal circuitry. And that is then supposedly used to just then program the ESP32.
When you say external driver, that's the 1K or no? What do you mean?
Sorry, no, the actual host driver you need to communicate with a USB device.
Ah, okay. So you have different, you don't use like standard FTDI driver, but their
exactly
own driver. Okay.
You get it off some dodgy site for this chip. At least that's how it used to be. I'm sure that's changed, but yeah, you can't use the FTDI drivers.
So theoretically, you don't know what is inside of the driver.
Exactly. It's probably stealing all your data and then sending off via this great patch antenna. But yes, something like that. I think.
How do you program or debug this microcontroller?
So it has JTAG as well, which I haven't exposed in this case. I didn't feel like getting a specific JTAG probe for this just yet, and I don't have like a Sega one, which I believe could debug this. So it's all via UART. You can change the boot mode to essentially flash the program.
There is a bootloader or something?
Yes.
Okay.
Yeah. And that works via this USB UART connection. And I believe you can download for the Arduino IDE like a package, a board support package for ESP32 microcontrollers. So it can be flashed, or you upload a certain bootloader to your ESP32.
But you can't really debug the chip. Or you can debug it. You can do it step by step, but you can debug it through UART.
Yes, debug. I guess, yeah. If you had the JTAG signals exposed, then you could set breakpoints and all of that stuff. But I haven't for the moment. Just to see if I can even get the basics running and then slowly move in. I mean, then, yeah, I haven't actually, I don't know if you tried one of those ESP32 development boards. I'm not sure if they have a debugger on it, like the STM32 boards have.
I don't know.
I'm not sure. Yeah.
I know the STM32 part of the board is the JTAG or something, usually.
Exactly. Yeah. And that is quite nice with those STM32 development or discovery kits, that they have a programmer on board. But yeah, I'm not sure how it is with the ESP32. But yeah, that's basically it. And this patch antenna is the one essentially we designed. And if KiCad works, maybe not, I can load my footprints, and all I've done to make that patch antenna is in my own library made this patch antenna by defining pads in KiCad. So I can just create a pad, change its properties, change it to SMD and then rectangular, and type in the dimensions. For example, for the main patch antenna, then for this feed line, and then for the microstrip.
So it has like 3 pins?
It has 3 pins, but I've given them all the same pin number. So it's all pin 1. And so basically these are all then linked together. And then in the schematic.
Okay, so because it makes it easier, so you don't have to draw the copper, which may cause some problems when you place it into PCB or something. I don't know.
Yeah, and then I can use this pre-made KiCad symbol, which is an antenna with just 1 pin. And then I just say this is pin 1, and then this maps pretty nicely to my symbol. I believe in KiCad, actually, I've drawn a trace, a very thin trace through this footprint, because KiCad doesn't see them as connected, even if they're like edge to edge. But this is of course invisible if you just draw like a 0.1 millimeter trace through. The DRC doesn't throw any errors.
I'm just curious, if you would place this track into the footprint directly, would it connect the pins or not?
If I place the track I put through here?
Yeah.
How do you mean?
If you put it directly into footprint.
Oh, that's a good, I'm not sure if you can do, that's a very good question. I should know better. No, I don't think you can place tracks in the footprint.
Oh, okay, so that's why you use the pads. 3 parts.
You can only use graphic lines, and I don't know. Yeah, the graphic line I don't think has any association with the copper. I'm not sure. Yeah, I don't think you can draw it. Yeah, so you have to do it in that way, which is a bit odd. But yeah, I'm not sure if Altium is different in that regard. If you can draw tracks,
you can, but I don't do that because I had always problems with it. And also, if you like import-export your design between different CAD systems or softwares, then it's going to make problems.
Yeah. Okay. Yeah. So that's the way I'm not sure if there's better ways or worse ways of doing this, but that seemed the most straightforward one in my eyes. But yeah, so basically I'm going to try and get this PCB manufactured, test it out, but I'm also going to make a second PCB, essentially the same circuitry on the right, but I'll be using this SMD chip antenna, again, with a very thorough test and comparison, if it works or if it doesn't work. So essentially just a little chip antenna. Unfortunately, most of it is in a language I don't speak. But it basically tells you, what feed lines you need, where you put the matching network, what dimensions you need. So everything for you as long as you follow it. So I'm going to give that a try as well, and then to see which one works. And then, of course, this will be a lot smaller, I believe. This is like a 1206 SMD antenna. So you'll save a lot of space. But it'll be interesting just to compare, at least function-wise, if they work. So that's another thing. I'll give it a little try.
I think there are also differences if you would like to make a product from this and you would like to go through certifications, then I think it's always easier to use module, which should be certified. But if you design your own antenna, I think it may cost you quite a lot of money to go through this certification process.
Yeah, no, that's a very good point. Yeah, I mean, it's a pretty ridiculous thing to do if you have pre-made antennas where you don't have to go through certification or things like that. But this was a kind of little just a test for myself, just to see if there's a little bit of fun. Exactly. So, I mean, hopefully it works. The signs are there that it should, but what does that mean these days? But yeah, no, but it was just a little experience just to go through patch antenna design, see a tiny bit of the theory behind it, and then also just explore the ESP32, and then hopefully be able to feature that in a couple of upcoming videos. Trying to break away a bit from the STM32 and try out some other things.
This was interesting. Let's see if it works.
Definitely.
It will somehow work. I'm pretty sure it will somehow work.
Yeah, maybe all of my devices at home will turn off when I turn this thing on. It just fries everything in the room. But yeah.
Then someone will buy it just because of this special feature.
Yeah. Ultimate in jamming technology.
And that's it. That's everything for today's video. I would like to say thank you very much to Philip for finding time to help me to create this video. Thank you, Philip. And if you have any questions, leave them in the comments. If you like this video, don't forget press the like button. If you would like to see my future videos, don't forget to subscribe. It helps a lot. And I would like to thank you very much for watching and see you next time. Bye.